All right, we are now moving on to talking about gravity and projectile motion. Biggest thing to know is this really falls under Newton's second law, so the equation we've been working with, F equals ma, is still going to apply here. So as we're talking about this, think about it in terms of how is the mass or the acceleration affecting the force, or how is that relationship all going? So let's first by just talking about gravity. And gravity is an attractive force between any two objects that depends on the masses of the two objects and the distances between them. So two key things here. You've got masses and you've got distances. Okay, universal law of gravitation is a pretty complex formula. You don't need to know that, but what you do need to know as the mass increases, okay, the gravitational attraction, abbreviate that GA, increases. So it's directly proportional. If the distance increases, the gravitational attraction is going to decrease. Okay, and that is all shown in the image here. So we've got there, and then this example is there. Again, mass and distances. So then what is gravitational acceleration? Gravitational acceleration is just fancy acceleration that is due to gravity. And we know that gravity accelerates all objects towards the center of the Earth, okay, towards that inner core. When we use the term up, we're talking about opposite of the pole of gravity. So when we use in science up or down, we're talking about with or opposing that force of gravity. Gravitational acceleration near the Earth's surface is 9.8 meters per second squared. Know this number. I cannot stress that enough, 9.8 meters per second squared. If we're talking about the force of gravity on Earth, you can automatically plug in gravitational acceleration as 9.8 meters per second squared. So, like I said earlier, we're just using Newton's second law. So we can find the force of gravity by F equals ma, plugging in our 9.8 meters per second squared due to gravitational acceleration to find the force due to gravitational acceleration. Okay, key word here, this free fall. When an object is only influenced by the force of gravity, it's in free fall. Okay, remember back in 2.3, we talked about air resistance, which is the force that opposes gravity due to the atmospheric conditions. So if we're talking about free fall, it has to be in a vacuum or in outer space to truly be in free fall. There are times when you have experienced something similar to free fall, though. Think about being on a roller coaster, those big giant drops, or if you've ever been in an elevator in a skyscraper, how it can go down very fast and you get that kind of flutter in your bellies. If you don't know what that feeling is, ask my daughter. She loves going down hills in the car for this exact same reason. So question for you here then. I've got a bowling ball and a marble. Bowling ball, large mass, large surface area. Marble, comparative, small surface area, small mass. So which one is going to hit the ground first if we drop them from the same height? The answer here is they are actually going to hit at the same time. Okay, remember when we're talking about falling, we are going to be talking about mass, okay, and acceleration, okay, force. So the acceleration isn't going to change here. 9.8 meters per second squared. So as long as they are dropped from the same height, they are both going to accelerate. Their velocity is going to change at the exact same rate. Okay, last week when we were doing lab, I talked to you guys about how when we added the sinkers, we were adding mass. This week we are going to start talking about weight. Very easy to get the two confused. Mass, how much matter is in an object, where weight is the gravitational force exerted on an object. It's the F in F equals ma for gravitational acceleration being the A. So because weight is a force, it's going to be measured in newtons. So we can now just change the formula around again and use weight as a little w, m being mass, and a being gravitational acceleration. Key thing here is 9.8 meters per second squared is on Earth. If I was on a different planet, Mars, Venus, or if I went to the moon, this number would be different due to the mass of the planet. Okay, so let's again talk a little bit more about mass versus weight. Mass and weight are not the same thing. Mass is how much stuff is inside an object, where weight has to do with the gravitational relationship between that mass and another object. So, mass does not change when I go to the moon, outer space, but weight does. Okay, because weight is associated with gravitational acceleration again. Let's clear up a little bit about this idea of weightlessness. Okay, a lot of times we see astronauts in outer space seemingly floating around in the space station or in their space shuttle. Okay, so we have this misconception that they are weightless and simply floating, but however, this isn't true because there is gravity. Okay, I need two objects. There is a gravitational acceleration right now between you and your computer. You both have masses. Very small gravitational attraction, but it is there. Okay, so in outer space, there's an astronaut, there's a space shuttle. Okay, even there's a gravitational attraction between the sun or between the earth, so they are not weightless. What they are in is, again, this idea of free fall, where gravity is the only force acting on the object. So they are actually falling around the earth in orbit. And when you are free falling, you have this feeling of being weightless, but you are not actually weightless. Okay, so what this really means then is the space shuttle and everything within it are falling in the orbit. There is no force to oppose that gravitational force, so everything then appears to float. One last big concept that this all applies to is then projectile motion. A projectile is any object that is shot or thrown through the air. It will follow a curved path due to the two forces acting on it. It has horizontal and vertical velocities. So it's going to go horizontally and it is going to go vertically. Okay, two forces acting on the ball. Downward force, I think you can easily figure out that is gravity. Okay, forward force. If I throw the football, it's really bad football, sorry, straight, okay, I have applied a force to that ball. It wants to keep doing what it's always been doing, Newton's first law. So it has its own inertia. However, gravity is also going to be acting on this ball. So it's going to actually follow a curved path like this. Now, if I were to throw this ball more into the air, okay, now I'm combating some of that gravity for a little bit because I've also applied an upward force. So I've now applied forces really in two directions. So that ball, okay, is going to go up until I've used all that force to overcome gravity, and then it will start coming down again. But again, it is going to follow this curved path because I applied some horizontal force to it. So here's just a computer drawing of what I was just showing you. Key thing is inertia and gravity are completely independent of each other. Okay? If there was no gravity and I applied a horizontal force to this object, it would keep going. Okay? But because we have gravity, it also pulls down. Different planets is going to have different speeds for this ball. More gravitational force, it's going to fall faster. Okay, so that concludes our lesson on gravity and projectile motion. If you have any questions, please let me know. Make sure that you are ready for lab tomorrow. If you have any questions on the lab entry ticket or getting your lab notebook set up, please let me know. Thanks. Have a great day.